Yeah, I stumbled across this one January 5th, 2022. FAST, the world's largest field aperture radio telescope, detects coherent interstellar magnetic fields. I would say the word coherent is really important to grasp. Magnetic fields, you don't get a magnetic field without an electric current. Anyway, let's dive into that quickly. Magnetic fields are essential but often secret ingredients of the interstellar medium and the process of making stars. The secrecy shrouding interstellar magnetic fields can be attributed to the lack of experimental probes. While Michael Faraday was already probing the link between magnetism and electricity with coils in the early 19th century in the basement of the Royal Institution, astronomers nowadays still cannot deploy coils light years away. No, but you could listen to Walt Thornhill, for example, and many others. Using the 500-meter aperture spherical radio telescope, an international team led by Dr. Li Di from National Astronomical Observatories of the Chinese Academy of Sciences has obtained accurate magnetic field strength in molecular cloud L1544, a region of the interstellar medium that seems ready to form stars. The team employed the so-called HI narrow self-absorption HINSA technique, first conceived by Leedy and Paul Goldsmith based on Arecibo data in 23. Chinese Academy of Science based on Arecibo data. Check it out. First they bring it down and then they use the data, make their own one. Anyway, fast sensitivity facilitated a clear detection of the Hinsa-Seaman effect. I have no idea what's that. The results suggest that such clouds achieve a supercritical state, i.e., are primed for collapse earlier than standard model suggests. Fast design of focusing radio waves on a cable-driven cabin results in clean optics, which has been vital to the success of the Hinsa-Seaman experiment, says Dr. Lee. The study was published in Nature today, January 5th. Yeah, it's still the 5th. The Seaman effect, the splitting of a spectral line into several components of frequency in the presence of a magnetic field, is the only direct probe of interstellar magnetic field strength. The interstellar Seaman effect is small. The frequency shift originating in the relevant clouds is only a few billionths of the intrinsic frequencies of the emitting lines. In 2003, the spectra of molecular clouds were found to contain an atomic hydrogen feature called HINSA, which is produced by hydrogen atoms cooled through collisions with hydrogen molecules. Since this detection was made by the Arecibo telescope, the Seaman effect for HINSA has been deemed a promising probe of the magnetic field in molecular clouds, or plasma filaments would be probably a better name for molecular clouds. Plasma filament. Okay. HINSA has a line strength 5 to 10 times higher than that of molecular tracers. HINSA has also a relatively strong response to magnetic fields and, unlike most molecular tracers, is robust against astrochemical variations. Astrochemical? Fast's Hinsa measurements put the magnetic field strength in L1544 at about 4. Was that micro? No. Macro? Macro? U? Gauss? i.e., 6 million times weaker than that of Earth. The combined analysis with quasar, active supermassive black hole, absorption, and hydroxyl emission also revealed a coherent magnetic field structure throughout the cold, neutral medium. The molecular envelope and the dense core with similar orientation and magnitude. Core, it goes through, or what do they mean that? Therefore, the transition from magnetic subcriticality to supercriticality, i.e., when the field can and cannot support the cloud against gravity, respectively, occurs in the envelope instead of the core, in contrast with the conventional picture. Oh man. How the interstellar magnetic field dissipates to enable cloud collapse remains an unsolved problem in star formation. The main proposed solution has long been ambipolar diffusion, the decoupling of neutral particles from plasma in cloud cores. The coherence of the magnetic field revealed by the Hinsa-Zeeman effect means that dissipation of the field occurs during the formation of the molecular envelope, possibly through a different mechanism than ambipolar diffusion. Yes, it's a C-pinch. Birkeland currents. You don't get a magnetic field without electricity. And in a way, the driving force is electricity, and the magnetic field is just, how to put it, byproduct of some sort. Not really. You don't get either of those. If you have a magnetic field, there has to be an electrical current somewhere, or currents. And if you have an electric current, you will have a magnetic field. And here they're talking even about plasma. Magnetic field, plasma. And they come up with this one. Yeah, I just really have to show a quick part of Donald Scott's videos about intergalactic Birkeland currents. And he briefly touches the black hole thing too. Enjoy.
There's what the velocity, profile velocity of the V looks like. This is, as you go out from the center of the galaxy, you get that. So you can solve, there's only one unknown in that equation, so solve for rho, and I don't know how you do it. You see, divide the square, divide both sides by the square root of r, and you end up with this conclusion. The charge density in this Birkeland current has got to be 1 over r. Well, it doesn't have to be, but if it is 1 over r, then we get the same velocity distribution that Fritzwicki measured. And if that's true, we don't need dark matter. The causation, the motivation to do this 85-year-long quest like Don Quixote, for this stuff that doesn't exist, really. We now realize if we only are willing to accept the fact that Birkeland currents twist, and that twist is the same twist that we see in the cross section of the galaxy, then that requires that the Birkeland current have this kind of charge density. This goes down as 1 over r. That's not any big deal. The magnetic field around a wire goes down as 1 over r. So there is lots of places that in science, at least in plasmas, that things, quantities vary as 1 over r. Well, okay, so here's the case where if the charge density in this Birkeland current is strongest at the center, and then tapers off as 1 over r, the velocity profile will be exactly what we're looking for. So, okay, I claim that's I was pretty excited when I found that, because that means that Vera Rubin can rest in peace, and we can quit looking for the chimera, what do you pronounce it, the non-existent ghost-like stuff that we never needed in the first place.
Yes. I have to admit, I don't get those formulas. I'm not a formula guy. But I spent some time with thinking about and reading about and watching things. You can watch galaxies. You can watch many things and recognize similar patterns. They're all over the place. And since they found now these coherent magnetic fields, this is just one more really important step for mainstream media to pick up in pace and realize what's going on. You don't get a magnetic field without an electric current. And if the magnetic field is coherent, therefore the electric current must be coherent too. Thanks. Bye.